Now I'd like to present the second part, radically shortened. Yesterday we already talked about the relation between topology and category, and I just want to make some further remark on, so to speak, the place of topology inside the net of categories. As was already explained, topology is of course not the only category, but there are many other categories, and the whole of mathematics may be considered as a net of categories. I'd just like to mention two other categories that have a special relevance for topology, namely the category of sets and the category of order structures. The category of sets, one may ask what are the objects and what are the morphisms of the category of sets. That's just the simplification of the topological case, namely in topology the objects are sets with topological structure defined by closure operators or whatever, and the morphisms are continuous mappings. In the category of set we just have naked sets without any structure, and morphisms are just the functions without the requirement of continuity. So there is a certain relation between topology and set theory, namely there's a forgetful functor. We simplify things, forgetting the topological structure, and the only thing that is left is the set X. And this relation between two different categories is a sort of function, namely a function that relates the objects of one category to the other category, and which relates the morphisms of one category to the morphisms of the other category in a regular way. I don't want to say more. The other important category for topology is, or that may be characterized as a category of order structures. The objects of the category of order structures are ordered structures. The objects of the category of order structures, again, are sets endowed with a certain order structure. Order structure should be transitive, reflexive, etc., etc. And there's an interesting correlation between topology, namely we forget about the points. That is to say, here we explicitly mention this, the set X underlying the topological space endowed with the topological structure. And the relation between the category of order structures is we only keep the set of, difficult to see? Okay, let's try it again. The topological space is mapped onto the Heiting arrow, but we only need the order. The order is set theoretical inclusion. If we have two open sets, then they may be ordered by set theoretical inclusion. So OX is not only a Heiting arrow, but more trivial, it's also simply an order structure. And the continuous map are mapped onto the inverse of this map F. So this is a correlation between the category top and the category this works because of the definition of continuity. You can check this. I mean, there's nothing behind it, but this is useful and maybe interesting relation between, here we have a continuous relation and here we have the opposite in this direction, and the general question is how much information we lose when we describe the topological space not by its points but only by its sets of open sets. Do we actually lose information, or maybe that this is just, do we really need points, carry points information, or are points just a superficial effect that can be ignored if we are interested in the essences of topology? And the surprising thing is indeed that we can, under favorable circumstances, we can forget about the points and keep only the open sets of points, and we can reconstruct points. Points are unnecessary for topology, and a somewhat outworn joke or pun defines this sort of topology which forgets about points as pointless topology, but a more friendly name is of course point-free topology. So in general, the task of topologists when dealing with general topological problems is to find out what is the structure of the net of categories to which the category top belongs. Finding interesting correlations between different categories. Not so interesting for instance, simply would be the relation that forgets about the topological structure. This is a trivial functor, it is said, but this one is highly interesting. And one may say that the origin of modern topology started with Stone's result, Marshall Stone's result in the 1930s, that there is an interesting non-trivial relation between lattices, order structures, and topology. I just want to mention this to describe the general context in which this takes place. So yesterday we learned that topology is an interesting, it's an interesting, enriching language, and we may say that it can be shown that also the language of category theory is an interesting language because it enriches our conceptual sources. Okay, so much about topology from a category theoretical perspective as a complementation of what we heard yesterday and as a partial justification why one may introduce the concept of category morphisms, etc., etc. Now I want to switch to a real application of topology. I want to talk about vagueness and borderlines, leaving aside refutability and falsifiability. And if we have time, I want to speak about the Stone representation theory. Yeah, I want to show that topology may be in a quite literal sense explicated and elaborated as a theory of vagueness. I start with a definition of vagueness that is quite commonsensical, namely, vagueness applies to predicates of ordinary language, but perhaps also of scientific language. Usually our predicates are vague. What does it mean? If we start with a standard Tarskian set theoretical semantics, a predicate may be represented extensionally as a set of its instantiations. In this way, the predicate red is represented by the set of red material objects, and the shortcomings of this approach are well known. For instance, the extensional approach does not distinguish between predicates with the same extension but different intentions. For instance, the predicates women and daughters apply to the same class of human beings living today, but the intentions of these predicates are nevertheless quite different, and these differences cannot be expressed in this sort of semantics. There are many other difficulties and shortcomings, and one of them is vagueness. Almost all predicates of natural language are vague predicates, and it's not clear at all whether this vagueness can be ignored in epistemological and philosophical considerations. Take red. Clearly, red is a vague predicate. There are cases of colored things for which we are not sure or we don't know whether they are red or orange or something in between. This state of affair may be expressed in different ways and may be explained by many different theories. Indeed, there's a huge literature of vagueness, and I have no time to go into it. I'm content with the following modest assertion. A predicate is vague if and only if it has a borderline case. The predicate is not vague if it does not have borderline case, and this may be expressed. The predicate is vague if and only if boundary of A is non-zero. This is a common illustration. So red is extensionally presented as the set of all red objects. Here are none. This box, for instance, certainly belongs to the extension of red predicate, but many other things, such as the blue, does not belong. And the borderline cases are things that are somewhere located here. So we don't know, or it's insecure or whatever, and at least they are not clearly red. And this situation, described in common sense terms, invites topologization, applying the apparatus of topology to render it more precise. It invites to topologize it because, we already have a strict and quite beautiful definition of boundary from yesterday. Boundary is the intersection of the closure with the closure of the complement. And this more or less directly leads to a topological theory of vagueness. I want to show that one may use the boundary definition, the definition of boundary, as a fundamental concept of topology. It's not necessary to start with closure operator or interior operator or open and close, etc. It is possible to describe topology as a theory of a boundary. operator. It's not well known. Most topologists say that it doesn't work as an intuition pump, but my point is to show that boundary is not a derived concept of topology, but may be considered as a fundamental concept, so that in terms of boundary, any other topological concept can be defined. The most simple case is, let us assume that we start with boundary. Some intuitive idea about boundary. Boundary is the set of borderline cases. Then we may define the closure operator in this way. This is just an application of the theory that we learned yesterday from the first lecture. But the problem is, what we would like to have is a well-behaved closure operator. A well-behaved closure operator is an operator that satisfies the four Kuratowski axioms. And certainly we must say something about the behavior of the boundary in order to get, by this definition, a closure operator that follows the Kuratowski axioms. And then one can show the following. The operator boundary, moving or mapping one set to its boundary, defines by this definition, defines a well-behaved closure operator if and only if it satisfies the following axioms. Namely, that the boundary of the empty set and the boundary of the universal set is zero. If A is contained in B, then boundary union A is contained in boundary A, union B, and the boundary of A is equal or smaller than boundary A. And the most surprising formula is this one, that connects the boundaries of two different sets, A and B, that calculates the union of the boundaries in this way. So, meditate a moment on this formula. It looks complicated, but it has some internal structure. The union of the boundaries is the boundary of the union plus the boundary of the intersection of A and B plus the intersection of the boundaries.
Excuse me, what's the meaning of
sorry, yeah, this is union as well.
Okay.
Sorry. Okay, I think this is clear, can be expressed in terms of well-known, yeah?
Just a short question concerning the second axiom. I mean, isn't this just the truth of set theory? You have A contains B, and then you add on both sides the same set. I mean,
I don't add the first...
B on the right-hand side, B
the
boundary of B rather than A.
Yeah.
Oh, sorry. Yeah, right.
Yeah.
Otherwise it
will be trivial.
Yeah. Because then it's not trivial. I mean, you may draw some X with closures and yeah, sorry. So this is trivial. This is almost trivial. Here, if you have A, oh. Yeah, then you immediately see from Euclidean space that this holds. This is a controversial axiom, actually, in our standard definition, because in some sources you find equality. For instance, in the well-known book of Casati and Varzi, Parts and Places, they claim equality, but this is not true. And this is, I think, new one. I know only of one source, namely the book I like, Kuratowski-Mostovski. There you find it here, this one. You find it mentioned by a rather obscure author named Stone as well, but not the famous Stone, another rather unknown Stone, and it appears as an exercise for topologists to find a proof of this. It's a sort of derivation formula, you may see. Yeah, so it's not too difficult to prove. I've proved it in some paper, but the proof is still too difficult.
Isn't there the pair of brackets at the end of this formula? Because I'm not sure about the order of operations at the very end.
Yeah, here should be a bracket.
Okay.
So the official version. So it's a calculation. You understand? Okay. So an operator from power set of X to itself is a topological boundary operator if and only if it satisfies these axioms. And then you have to prove if you define a closure operator in this way, then this closure operator is or satisfies the Kuratowski axioms, and the corresponding boundary operator of this closure operator is again this one. So it goes in a circle. It doesn't matter from where you start. You may start from boundary or you may start from closure, but this leads interdefinability between both.
Sorry, could you give an example illustrating the necessity of the third part in this last axiom? I mean, this intersection of border of A and border B, because I somehow can get around this problem. So why do we need this third part? Because in some cases it's not necessary, but in some apparently it is. So
yeah, it is. You may. It refers to some examples that we already discussed. The usual culprits, the usual people that are guilty, the usual guilties. Namely, take Q, the rational numbers, and I, the irrational numbers, that is to say, the complement. Then we have the boundary of A and B. The boundary of A and B is empty. No, it's the entire rational real numbers. So we have R union R is the boundary of what? Q CQ. The boundary of intersection Q with its complement is 0, and so this is 0. The same applies to, or the union, sorry. Here, this is clearly empty. This is empty as well, but yeah. Yeah, as I said, I'm not sure whether this is topologically relevant. But at least it is, whether it is philosophically relevant, this relation. But if you subscribe to this definition of boundary, as virtually all philosophers do, then you have to accept this consequence. So, in what sense then topology yields a matter of a theory of vagueness? We simply define a closure operator in this way. And so what we can do is, remember here that boundary was defined intuitively as the set of borderline cases. We start with an intuitive understanding of borderline cases and obtain a topological structure of our space of possible worlds by accepting a borderline operator, that is borderline cases that satisfy these four definitions. The problem is, that there's widespread opinion that the borderline operator, the boundary operator, satisfies quite different conditions. Here we have the one of the book of Parts and Places. This is the same. Here we have a stronger condition, and here we have a simplified condition. And moreover, it is claimed that these conditions are equivalent, quote, to the standard Kuratowski axioms. But this is not true. The situation is somewhat different. Here are some further counterexamples. What really happens, or what really is true, is not what is not valid is this one. The boundary is boundary, as it's more or less common sense. But what obtains is this strange formula. The boundary of the boundary of the boundary is the boundary of the boundary. Many people in vagueness theory maintain that this iteration of the boundary goes on and on. But this is not the case. It stops at the third level. So this is a sort of philosophical puzzle, what to do with this strange equation. If you accept the standard definition, and almost everyone does, and nobody has an idea of how to redefine a boundary in a reasonable way. So when we accept the the standard definition, we are forced to accept this one.